I'm sorry. How come when I became mute? Hello? When I became mute, I explained everything on mute. Oh my God. I'm sorry. I'm extremely sorry for that. Give me a while. Okay. So today we are going to learn about elimination reaction, right? So in that NaOH and KOH would be present. These are in alcoholic form, right? So the basic difference in between alcoholic and aqueous is what? Whenever OH is in aqueous form, it acts as a nucleophile, right? And nucleophile, it's electron-rich species. It attack on an electrophile, which is electron-deficient species, which we have learned into SN1 and SN2 mechanism, correct? And whenever OH group is alcoholic in nature, it acts as a base, right? What is the tendency of base? These base abstract a beta hydrogen from your substrate and form a carbon-carbon double bond. What does it will form? It will form a carbon-carbon double bond. And hence, it eliminates the hydrogen from your substrate, and hence this is called as an elimination reaction. Clear? Understood? Fine. So general mechanism, I'll explain you about it. Okay. I'll explain you the general mechanism for this. Suppose this is a carbon-carbon single bond. Okay. It has your halogen, and here it will be the hydrogen. Here any other alkyl group can be present. You can consider. Right. So what is the functional group among this? This is halogen. Halogen is your functional group. Okay. So now what would be the beta carbon? The carbon on which functional group is present? Fg. Fg is nothing but what? Functional group. The carbon on which functional group is present, that is a alpha carbon. And the adjacent carbon of the alpha is nothing but beta. It can be either left side or right side. Okay, it can be either upside or downside. It doesn't matter. Okay, but then the next to the alpha carbon would be beta carbon. And if that beta carbon has a free hydrogen, this hydrogen would be abstracted by your alcoholic KOH. If there is a KOH or OH group, which is basic in nature or alcoholic in nature, what it will do? It will take this hydrogen. This hydrogen will be donated its electron over here. It form carbon-carbon double bond. Your halogen would be depart. So this is a basic mechanism. You will get what? Carbon double bond. Here would be your new compound form. And here your K will go with X, and OH will abstract the hydrogen. It will form the water molecule. Correct? Yes or no? Or else you can say your base will be take this hydrogen, and your halogen would be released as a leaving group. You can say like that. So you'll get BH plus X minus. This would be your general reaction, right? What would be case when if there is more than one beta hydrogen is present in given compound? If there would be more than one beta hydrogen is present, that time which product would be formed in a major quantity, that we have to learn, right? Shall I erase it? You understood this? If you want to write, let me know. Fine. So I'm going to erase it. Fine. So I have one example with me. Okay. So that example would be CH3, CH2, then CH2, then CH, then CH3. Okay. And it has a Br over here. Br is nothing but halogen. Okay. And it's your functional group. What it is? It's your functional group. So alpha carbon, this would be a beta carbon, and this is also your beta carbon. So both the beta carbon has the hydrogen, isn't it? Yes. So which beta hydrogen would be abstract? There would be the two possible products, right? So that I'll show with different color. That would be convenient, I guess. Fine. You can see Here also beta hydrogen present, and here also beta hydrogen is present, right? Now, what happened if this CH and here one more H, I will write it in this manner. This hydrogen would be abstract by OH minus, right? If this OH minus abstract this hydrogen, it will donate its double bond in between alpha and beta carbon, and you get the double bond in between this alpha and this beta carbon. So what you will get? What you will get over here? CH3, CH2, CH, as hydrogen has been lost, carbon-carbon double bond has been formed, right? As here double bond is formed, this Br would be depart. You will get again CH, okay, Br is lost, and here it is CH3. This is your first product. What happened into the another product that I'll show with a different color. That would be also like better understanding for you. Now you can see here CH3. So I will write here CH2 and one more hydrogen I will write here in this way. So if this beta hydrogen would be abstract by the OH, right? What happened? It will donate its double bond in between alpha and beta carbon. It will form a double bond and this your bromine will be depart. Now product will be what? CH3 as it is, CH2 as it is, here CH2 as it is, here CH, Br is lost, double bond CH2, correct? So if we have to label it, what would be the name for this compound, second compound and first compound, check? What would be the nomenclature? You can see here, 1, 2, 3, 4, 5. 5 carbons are there, right? At the second position, there is a double bond. So it will be pent, 2, in, correct? And here if we see 1, 2, 3, 4, 5. At the first position, double bond is there. So it will be 1 pentene or pent 1 in, correct? Pent 1 in or pent 2 in. So among these two, only one is the major product. So which one is the major product? And why? Can you guess the product, which one is the major and why? Mm-hmm. Yes, no, at least tell me yes or no. If you can't, I'll give you hint. Chandana, am I audible to you, beta? Okay, I'll give you hint. So we have learned about the Markovnikov and Sedzev rule, right? Yes or no? For the substitution reaction. More substituted product would be the major product. Yes? So the carbon-carbon double bond is a more stable when there is a more alkyl groups are present or attached to the carbon-carbon double bond. If you see this product, on this carbon-carbon double bond, there would be the more alkyl group. Here is one and here is also. Then if you see here are the hydrogen and this side only alkyl groups. So more alkyl groups are present in this, right? More substituted alkene would be your first product and hence it is major, right? And this will be minor. You can follow a Markovnikov's rule for this. One of the scientists, the name is given. What is that name? Alexander. Wait a minute. Let me go through it once. Yeah. Yeah. Alexander Zestev. He is also called as a Sedzev. In 1875, he formulated a rule which can be summarized as in dehydrohalogenation reaction, the preferred product is that alkene, which has a greater number of alkyl group. So in that you can see there are the greater number of alkyl group and here are the less alkyl groups and hence it would be the major product and this will be the minor product. Fine? Clear? So shall I erase it? Okay. Now see the next. Oh, Control Z. Fine. Done? Yeah, fine. Now, the next one would be, you can check about the reaction with metals. Okay. In that, first thing which we have to see, that would be Grignard's reagent. Right? So what it will be? R Mg X. How it has been prepared? In the Grignard reagent, carbon magnesium bond is a covalent bond. This bond is what? Covalent bond. But it will be highly polar. This will be electronegative and this will be electropositive. This is minus delta and this is plus delta. Keep it in your mind. And this is also minus delta. Fine. So with the carbon pulling electrons from electropositive magnesium. And hence, this is the reagent where alkyl group act as a electronegative element. And hence, it can be attacked onto the electrophile. Understand? Highly few reagents are there in which alkyl group act as a electronegative because it is a carbon. Alkyl group is made up of carbon and mostly carbon is electropositive in nature. But then Grignard reagent and the copper reagent only would be there. Cuprous reagent only would be there in which whenever it link with the copper or with the magnesium, it become electronegative. Understand? So this is one of the important reagent. One of the important reagent, okay, that you need to keep it in your mind. Now, the reaction of this Grignard reagent, we are going to see what happened when it will be react with R, Mg, X when it react with water, H2O. What will be happen? Any guesses? Do you have any guesses? What happened when Grignard reagent will be react with water? No, fine. So, whenever Grignard reagent has been reacted with the water molecule, it will take a hydrogen and will form the alkane, right? So this is one of the reaction in which we are able to form the alkane. Understood? Fine. So what happened exactly in this? R will take H from here. So it become alkane. And here, your MgX will be as it is and it will attach with OH as well because this OH would be come out from here. H will go with the R, right? And OH would be goes with Mg because it is electropositive. So OH will act on it. This electronegative element, electronegative group of the element will go to the with Mg. Okay. So this is your side product. So you will get alkane as a product. Fine. And what happened when your alkyl halide has been reacted with the sodium in presence of dry ether? Right? That reaction is nothing but a Roots reaction and already I have explained you about it. Correct? Yes or no? So when your alkyl halide Rx reacted with sodium metal Na, right? 2 moles of alkyl halide react with 2 moles of sodium metal. You will get what? 2 moles of NaX. And this R and R will be coupled with each other to form a higher member of alkane. Means whatever member of alkanes you have started with, you will get the exactly double. Okay, suppose you have started with ethane, you will get the butane. If you started with propane, you will get the hexane. Means suppose you have started with 1 number of carbon atom, you will get here 2 number of carbon atom. If you started with 2 number of carbon atom, you will get 4 number of carbon atom into the product. And this reaction is called as what? Roots reaction. Right? And this reaction would be takes place when, see, in this, what happened? Alkyl halide react with the sodium in a dry ether. Here, one of the important thing is what? Dry ether. It's very, very essential. It is a medium for the reaction. Do not forget about it. This is a Roots reaction. Fine. Now, we are going to see the reaction of haloarenes. Have you done with this? Roots reaction you wrote? We have seen the mechanism also for this, isn't it? I have explained you in the question answers. Once we have seen the 15 question, Among that, one of the question on Root's reaction. Fine. The next one, nucleophilic substitution of haloarenes. Nucleophilic substitution of okay. Now, if you see the haloarene, this would be the haloarene. Okay, this is your benzene aromatic ring with double charge, and here it will be your X, right? And here it will be nucleophile. So nucleophile have an electron pair. It's electronegative in nature. Your haloarenes are also electronegative in nature because this is electronegative, right? If it is electronegative, it will be passed the electron over here, and over here. Means your ortho, para, and ortho position is electronegative, isn't it? In this your hybrid, suppose you have done it here hybrid, it will be X with positive charge, right? So negative, negative, they would be repulsion. So hardly your haloarenes undergo nucleophilic reaction. It will not undergo nucleophilic reaction. But then yes, in a drastic condition, if you don't give any sort of choice to that particular molecule, definitely it will undergo reaction, right? But then it won't have a proper yield, right? In a drastic condition, you may get the product. So what sort of product you will get? Check. Suppose in a drastic condition, you ask it to undergo the reaction. Replacement of halogen group we are going to do with the hydroxyl group, suppose. This would be your reaction. It's a benzene. It's a chlorobenzene. It's a chlorine, right? It will react if NaOH, right, at 623 Kelvin and 300 atmospheric pressure, right, in the presence of H+. What happened? You will get the OH. So you can see the conditions. There would be 623 Kelvin temperature, 300 atmospheric pressure. So forcefully, you made this OH to replace by Cl. And then only this nucleophilic substitution would happen in this case. And this reaction would be become more favorable or more easy when your means one of the substituent on the benzene become nitro group. So what is the function of nitro group? Nitro group is electropositive in nature and it withdraw the electron from your benzene ring. And hence your ortho, meta and para position to that particular substituents become electropositive. I'll let you know how. Suppose the same ring is there. Okay. So same benzene ring on which your chlorine is present. And if at its para position, I have introduced the nitro group. So what is the role of nitro group? It will be, if we draw the electron from its ortho, it become electropositive. It become electropositive, isn't it? And even its meta position also become electropositive. So here what happened because of that, as it become electropositive due to nitro group, its ortho position would be electronegative more, and your nucleophile would be at here, and then bond would be shifted, and hence your compound would become stable, right? Yes or no? So finally, you will get the product in what sense? In this way. Here also again NaOH you have to use as a nucleophile OH you have to use. So NaOH need to be introduced. Your temperature would be reduced over here. It becomes 443 Kelvin. Okay. And H plus you have to add at last to satisfy your carbocation. Later, you will get this Cl as it is. And here it will be NO2. Clear? And the same, if your nitro groups are increases, suppose instead of single nitro group, there would be double nitro group or the triple nitro group. So efforts for the nucleophilic substitution would be less and rate of reaction would increases. that you need to keep it in your mind. Understanding nitro group make benzene ring more electropositive, and because of that, nucleophilic attack of OH minus on the ring would become easy. Clear? Understand what is the nitro group? It is electron withdrawing group. Okay, it will withdraw the electron from the benzene ring. So benzene ring become electropositive, and hence OH may attack on it, and you will get the product. Here you will get OH, I guess. Not over here. Yeah. And hence you will get over here OH. Fine. Clear? Chandana? Yeah. So OH would become at the in the replacement of Cl. Fine. And rate of reaction would be again increase. How I'll let you know. Shall I erase it? If instead of one nitro group, there would be 2 or 3 nitro groups present onto the benzene ring, it will increase the rate of reaction. Suppose here is a nitro group NO2. Here is your chlorine. Here is your NO2. Again, your condition become more easier. Obviously, you need an NaOH. Okay. Apart from that, you have to reduce the temperature 368 Kelvin. Okay. And H plus you need to introduce to balance it later. What happened? This would be benzene ring. Cl would be replaced with OH. Na2 and NO2 would be as it is. It become your electron rich benzene ring more electron deficient by withdrawing the electron from benzene. And the same for the trinitrobenzene as well. Halo derivative of trinitrobenzene. So here it will be NO2, NO2, and here also NO2. Right? What you will require over here? Same NaOH. Just you have to warm. You need not to heat it for the particular temperature. You have to just add water. Easily it will be replaced with OH. So what you come to know? If electron withdrawing group would be introduced on the benzene ring, it will undergo nucleophilic substitution reaction very easily as compared to without electron withdrawing group. That you need to keep it in your mind. Maybe rate of reaction may ask which will undergo the electrophilic substitution faster. So nucleophilic substitution faster kind of example would ask in your JEE. So this kind of examples, this kind of things you need to keep it in your mind. If electron withdrawing group would be increases, nucleophilic substitution reaction become more easier. And if electron withdrawing group would be increases in the electrophilic substitution, that time that reaction would become more difficult. Understand? This is a nucleophilic substitution. Now we are going to see about the electrophilic substitution. Clear? Fine? Okay. Now next one. We are going to see about what? Electrophilic substitution reaction. Okay, of haloarene. Okay, so if you see the haloarene, here suppose halogen. As we know that it is electronegative in nature, so it will be form electronegative character at the position ortho, para, and ortho respectively. Correct? And hence this center would be act as an electron donor, right? And electrophile are electron receiver, and easily can be covalent bond would be formed, right? It can form easily covalent bond. Now we are going to see first of all halogenation, how monochloro would be converted into dichloro compounds, that we have to see, right? So for that we need a Lewis acid catalyst, right? Lewis acid catalyst we require. For that reason, we will use either FeCl3 or AlCl3, right? FeCl3 or AlCl3. Either you can means any halogen, not Cl3 or only Cl3 we should use. It's not like that. It should be either FeX3 or AlX3. Any halogen would be there. Okay. So if I'm going to form a dichloro derivative of benzene, suppose one chlorine is there present over here. Okay. And if I have to add one more chlorine, so directly Cl2 I have to add in presence of Lewis acid catalyst. That would be anhydrous FeCl3. So what is the role of this FeCl3? I'll let you know. Anhydrous means what? It does not have a single drop of water. Understand? Means completely free with water. If water would be present, this reaction will not take place. So in the first step, what happened? When you add a FeCl3 with Cl2, Cl and Cl, this will form a bond with the Cl. So it will become in this manner. You will get FeCl4 bonded with Cl. So this is electronegative and it become electropositive. Clear? Understood? Now this, whatever reagent, mediator reagent which has been formed, it will be reacted with your benzene ring. Halobenzene. Okay. So what happened here? It will be chlorine. As we know that its ortho position is electron rich and even the para position is electron rich. So it will be act on what? Your this FeCl4 and Cl. Right? This is negative, this is positive. So it will be act on positive charge and this FeCl4 would be removed. So you will get what? Mediator in this way. Intermediate product. Okay. It will be here. As bond has been removed over here, it become electropositive and new bond will be formed with your chlorine. Okay. Here nothing is what? Hydrogen. Hydrogen would be present. Clear? And then this would be your rate determining step. Okay. This is your RDS, rate determining step. Okay. And it will be, it is called as it will be decide the kinetics of the reaction. Rate of reaction is completely depend on this step. Okay. Because this is a slow step. And what happened in the next step? Whatever intermediate has been formed, okay, this intermediate in very fast manner, this hydrogen would be loose, okay, and you will get dichlorobenzene. This is fast step, minus H plus. Cl and here also Cl. Clear? So this is dichlorobenzene, means monochlorobenzene would be converted into dichlorobenzene. So this is not a major product. It's an ortho product, so it's not a major product. Another possibility is what? When bond has been given from here, that time what happened? Attack would be happen at the para position, isn't it? So another product would form. It will be in what case? I'll let you know. Aditi, are you there? Hello, are you there? Yeah, that is more important. Otherwise, only I'm babbling, and at last I would come to know that Aditi has been Chandana has been disconnected. It should not be happened, right? Fine. Now, finally, what happened? Another reaction at the para position. I'll let you know the mechanism for that too as well. So, suppose this would be your monochloro derivative, right? And here would be your Cl, your FeCl4 with negative charge, and here it will be positive charge. Wait a minute, huh? It will be attacked. Wait a minute. हेलो अस्सलाम वालेकुम मैं क्लास में हूँ मैं 5 मिनट में फोन करूँ हाँ 5 मिनट में लगाते लगे now what happened here attack would be happen you'll get the para derivative how I'll let you know so your intermediate would form here Cl okay so your Cl would come at this place and it become electropositive and here it will be hydrogen is present clear and another part this is slow RDS slow step and here minus H plus would be taken okay happen This minus H plus would be formed here double bond, right? And you will get the para derivative of dichlorobenzene, Cl and Cl. In this way, your product would form, right? Yes or no? So if attack would happen at this place also, symmetrical product, ortho dichlorobenzene would form, and this is para dichloro product would be formed. But then para dichloro product would be major and ortho product would be minor. What is the reason behind it? It's all about symmetry of product. Okay. If you see, you are able to cut this product in two halves in an equal manner, right? From here you can cut. So it is symmetric product and hence it has a more stability as compared to this one. And hence it's a major and this is a minor. Clear? Yes? Aditi? Sorry, Chandana, I'm sorry. Aditi is not there, Chandana is there. I'm extremely sorry for that. I hope you understood clearly. Yeah. So there are a few more reactions, like we have to learn about the sulfonation. We have to learn about the FC alkylation, FC acylation.